Next lecture, atomic force microscopy by Denis Alikin. He is specialist in IFM. He worked in Ural Federal University, Russia, and in our university too. He is specialist in atomic force microscopy, and he have a lot of results, ferroelectric, piezoelectric, composite, and simple crystal. Okay, please start.
Okay, thank you for introduction, Igor. So today I'm going to talk about the atomic force microscopy, and I think it will be a basic talk about the main things, how to operate IFM, what kind of modes IFM usually have, and how to implement them to get really quantitative measurements by IFM. And if you have any more questions about some specific modes, so you may ask me in real life or by email, so I can also address your questions later. So first of all, I want to briefly mention what is the difference between the electron microscopy and atomic force microscopy, because from the point of researchers, it's who are not really involved in this object, they looks really similar, and it is reasonable because they have more or less the same resolution. So it's a nanoscale resolution, so you can easily visualize objects and to see some topographic things. But there is nevertheless a principal difference between these two techniques. So electron microscopy is usually operate with electron beam scattering in the material, and actually what we see on the images of scanning electron microscopy, it's just a quantity of electrons which can be registered by the detector, and operating with these electrons allows us to understand how the material behaves structurally, and it allows us to understand what is the chemical composition and some structure of the material. On the other side, the IFM, it's a bit different story. So IFM allows to work with the functional properties. So it allows to measure the same characteristic which we usually measure in the macro scale by the known techniques. So in each point of that image, we actually somehow plot the value of some physical quantity, and that is why we call this method the functional microscopy. So, and the reconstruction of the image is just a representation of the real data which we capture from the measurements in the real world. So, what is the motivation to use atomic force microscopy? So the motivation to use atomic force microscopy is just because we want to know the properties of the material at the nanoscale. So, and in order to get insight in this measurements, we need somehow to decrease the sizes of the electrodes, probes, or some measurements elements, and the atomic force microscopy is expansion of the classical methods to the nanoscale. So we can do different kind of measurements like nanomechanics measurements, nanoelectromechanics, local electrical properties, local magnetical properties. So this is not all the list. So each year there are different modes, new modes are introduced in the literature, and for sure most of the properties which people measure in macro scale, the measurements, the analog measurements can be done in atomic force microscopy as well. So the key component of the atomic force microscopy is the cantilever. The cantilever, so since 1986, I think there is a quite rapidly increasing commercial production of the cantilevers based on silicon mostly, but there are absolutely different configurations and geometries of the probes, and this is really depends on task. So if you need to operate some specific or measure some specific quantities, you may create your own tips. But since 19th, it's become more easy to operate with IFM because we can buy tips. They're not too expensive, and for most of the aims, we use normal silicon tips created from the silicon by the chemical etching, and this is a list of the parameters which we usually have for the atomic force microscopy tips. So one of the main parameters is the stiffness of the tip, because the stiffness demonstrates how the tip interact with the force which applied to this tip. So we can bend the tip by the applied force, and the stiffness demonstrates how much tips bends under the action of the force. And we also have some resonance frequencies, which also very important, because the position of contact or non-contact resonance can be used to amplify the electromechanical signal, and thus it can be used to improve the sensitivity of the methods. And we also have such parameters as the radius of the tip and angle of the tip, and also we could cover the tip by the different kind of coatings. So it's important, if you want to do some electrical measurements, you should deposit some metals, or if you do some magnetic measurements, you should deposit some ferromagnetic coating. And the fundamental basics of the atomic force microscopy lies in the van der Waals force interaction between the tip and the surface, and this realized. So you know this, I think, potential curve, and we see that there are different regimes of the tip surface interaction. So it can be a repulse regime or attractive regime, or it can be some so-called intermittent contact or taping contact, where you have the oscillations between different regimes. So actually, the operating in some specific forces and some kind of tip surface distances allows us to study absolutely different objects. So if you work with more or less normal objects like a classical ceramic materials, or some films or single crystals which are really stable, so we can use a normal contact mode, and this gives us really pretty high resolution. And if we work with some soft objects, so we need to do some really precise measurements, like measurements of nanomaterials, it's better maybe to use softer tips, and maybe it's used to operate in attractive regimes. So when the interaction between tip and surface is not so strong. So we will discuss a bit about that later. So first I will start with the contact mode AFM, so the basic mode of AFM. And first we need to consider the schematics of the atomic force microscope. So the atomic force microscope is the cantilever itself, so it's made from silicon. Yeah, so this is some tip with the diameter of a nanometer, and we put it in the contact in the surface, and we have some interaction. So this interaction usually can be detected by the optical laser deflection system, so consisting of the laser photodiode, and we have some feedback system which also will be discussed further, and we have the scanner. So actually the atomic force microscopy is a part of the scanning probe microscopy techniques, and it means that in order to get a whole image, we need to organize scanning, so to measurements of the signal in each point of the scan. So for that reason, we move the sample very precisely by the scanner on the with the sensitivity of a picometer. So and actually we register the signal in each point, so which is denoted by the red dots in this image, and we move the tips point by point in order to get whole scan, and we usually call the fast scanning direction and slow scanning direction as fast scanning axis and slow scanning axis. So on each point we have some measurements value, and after that we can represent it's like an image. Let's say some words about optical beam deflection system. So what is the optical beam deflection system? Actually, if we have some interaction on the action of the van der Waals force between tip and surface, we have we somehow need to register that the tips bends or somehow have a inside what kind of force acts on the cantilever. And for that reason, we use a system consisting of the laser and photodiode. When we focus the laser beam on the surface of the cantilever, we can put it inside the middle of the photodiode, which consists on the force action. And under the action of the force, the spot inside the force action photodiode can be moved up and down or left and right, depends on what kind of force acting on the cantilever. So actually it means that the cantilever have a different modes of bending. It's called bending or twisting or buckling. And in order to register this shifting, we usually create some signals, electric signals. So one is the deflection signal, which is, can be described by the formula which you see on slide, and we have also lateral signal we describe as another formula. So actually it means that we have separate registration in each section of this photodiode, and we can precisely set how much the spot moves in any direction of the photodiode. And the physical meaning of this motion of the spot is actually the value of the cantilever bending, which we'll talk after. And in order to collect signal and create images, very often we use the so-called forced constant force mode or mode with feedback. Why we need that? Actually, it's because of when we put the tip in the contact, so we move it across the different features of the relief, and if this feature is too high, so it may actually break the cantilever, and that is why it's better to keep the same distance between the tip and samples, also to keep the same force. Yeah, to organize this operation, we usually use so-called feedback system. So it means that we move the tip across the surface, and then when we have the increasing of the force between tip and surface, we just a bit move up the tip, and this allows us to get a deflection signal constant all the scanning, and the changing of the tip distance between tip and the surface allows us to construct a real relief of the surface. And for most of the applications, the regime of the constant force is preferred because it's less damageable, and you can save both tip and the sample from the too much interaction with much force. And actually the correct setup of the feedback is very important to get a really nice and high quality images, because it's very clear influence on the what we see on the final images. So for example, here there is an example of the step. So in the bottom part of the image we have a real step which we measure, and then the up part of the image is a deflection system, so it's reflects how the tips interact. So you see that most of the scanning we have a constant signal because we are keeping constant force, but in the places where we have rapid change of the relief, we have error in the feedback, and this error is the feedback we just trying to compensate as fast as possible. And if we have really good calibrated feedback systems, we have such image which we see now. But if we have some problems with the feedback, for example, we put the coefficients of effect too slow, it will results in a smoothing of the relief, so we will have a deflection of the relief from the normal one. If we on the opposite side increase the coefficients of the feedback too much, so we will see the oscillations in the image because the system becomes to excite itself, and this is also bad because it's also change the real contrast of the images. This is kind of examples of different materials which were studied by the atomic force microscopy, for sure studied by the basic mode, so we just visualize the relief. So on the left side we see that we can visualize atomic structure, atomic topography of the material. On the right side you see that the risk can be done in the mesoscale, so the micrometer scale. And actually what we see as an image is not just a simple image like in optical microscopy or electron microscopy. It's a signal of the change of the height in order to keep the force constant. So it's more or less functional image as well. And actually we talked about the deflection systems, deflection signal, and this signal is really nice. It allows us to construct very nice images, but we want also to know how much the cantilever displaced under the interaction with the relief feature, or we also want to know how much force we applied. And for that reason we need to calibrate our system, and this is a really important point, because usually the signal from the photodiode is we can measure it in the nanoamperes or millivolts, depends on the microscope you have. But what we really want to represent in the scientific papers with some real quantities, and in order to calibrate, we have two procedures of the calibration of the cantilever. So we need the sensitivity calibration, and we need the characterization of the cantilever properties, so the stiffness of the cantilever, which we told before. And how it's possible to be done? So we start first with the conception of the force curves in IFM. In IFM, actually we told that there is some van der Waals force, but actually it's not only the case. So when we put the tip in the close connection with the surface, we can actually raise absolutely different kind of forces, such as adhesion forces, capillarity forces, hydrodynamic forces, and much more. And what we actually do, we can just measure the dependence of the force under the distance between tip and surface. And what we see, it can be such kind of curve. Yeah, so in the right side of the curve we see that there is no any change of the force with the distance, and it means that we don't have any interaction between surface and sample. And if we move down to the surface, so it's a left direction on this slide, so we see that after hysteresis appears a linear dependence between force and distance, and instead we are in the range of the Book law, so we have a change of the force linear with the distance. And actually this makes sense. So, but the question is, what kind of history is what we observed in that curve? And this hysteresis is usually happen because of the specifics of the interaction between tips and surface. So if we don't have any other forces instead of van der Waals, we will see only the linear dependence without any hysteresis. But if we have some other forces, like an adhesion, for example, we always have a liquid layer at the surface, and this liquid layer create additional attractive force between tip and surface. And this actually, when you move tip, you doesn't feel so much this attractive force, but when you retract the tip, so you will see that you have some force which play against your applied force, and this really creates these hysteresis properties. And this is also very important because it allows to measure us not only the van der Waals forces, but as well some forces connected with the properties of the nanoscale material which we study. For example, in this image you will see the different molecules which were studied by the applying and measurements, applying force and measurements for distant curves, and you see that the opening of the hysteresis depend on the chemical composition of the materials deposited at the surface, and thus we can quantify this adhesion force and to study the adhesion properties of the different kind of films. On the other case, it should be considered that in any interaction between tip and surface, we have actually two elements which is depicted here on the screen. So, and we have actually two serious stiffness. One is the stiffness on the cantilever itself, and the other stiffness of the sample. And when we do the measurements, we need to take both in account, both of these stiffnesses. And if we want, for example, to do the measurements of adhesion force, our cantilever should be not so stiff, because we need to measure the stiffness of the sample. On the opposite case, if you want to measure something, some properties of the sample connected with the indentation, so with the hard materials, we should use the hard cantilevers, which can be easily push on the surface and to measure the response. And why we told about these force distance curves? Because we also need somehow a way to calibrate the cantilever, and the best way how to calibrate the cantilever is to use very stiff material. For example, to use some silicone or use some really stiff metal or glass, and in that case you will not have any deformation of the surface under the action of the tip, and you have only deformation of the tip itself. And it actually is a good way to calibrate the cantilever, because when you measure this force distance curves, it will look like on the slide. So you don't have any hysteresis, you have only linear slope, and actually these slopes allows to understand the coefficients between of the changes of the signal of the photodiode and the changes of the cantilever displacement in nanometers. It helps us to calibrate the tip, so the tip sensitivity. On the other, sorry, I will return back to this slide. Maybe. Yeah. So this is the first step which we discussed on the left side. On the left side of the image, so the calibration of the signal sensitivity, and after that we can go further and to characterize the forces, because we need also the stiffness of the tip in order to understand how much forces we pressure on the surface. In order to understand that, we usually use so-called thermal approach. I will not go to the details now, but this is based on the measurements of the cantilever resonance, and the position of the frequency allows us to estimate. It's directly linked to the spring constant or stiffness of the cantilever, and gives us the understanding how much stiff our cantilever. This is important because not in all the cases what you read on the box of the cantilever, where usually manufacturer gives some values of the stiffness for the cantilever, it's not actually the real stiffness, because in the production process you have a deviation from this stiffness because the production process has some differences in any case. So when you have these two coefficients, so one is the sensitivity or inverted sensitivity, and the other one is the spring constant or stiffness, so you can actually quantify your values and to have an understanding how much tip displaced under the action of the force and how much force you applied. And this is really important because it makes the atomic force microscopy, especially quantitative technique, which can be used to measure the quantitative values of any physical properties. And the other important points, that if you're gonna choose cantilevers, you should see on your aim, specific aim, because independent on what kind of sample you are studying. For example, you are studying some stiff sample or soft sample, so you should change the stiffness of the cantilever. If you work with soft samples, it's better to use soft cantilevers, and if you work with hard samples, better to use hard cantilevers. This is a general law, but there is also some exception. I mean, if you need to organize some specific task, so it may be you need to control it more carefully. And we also have, okay, the next thing which we should talk is special resolution of IFM. Special resolution of IFM. So actually IFM has quite high special resolution. It depends on what kind of resolution you are considering. If you need to have a resolution in Z scale, so this resolution is extremely high, so it can be in picometer scale. And if you work in the lateral resolution, the main thing which determines the resolution is actually a tip radius. So if you have really sharp cantilever, you can see really small things of the relief. So usually the conventional tips, it's from 1 nanometer to 50 nanometer. So it means that your lateral resolution is limited to these values. And actually, as you see in the image, so whatever you're measuring in IFM, it's just a combination between the tip shape and the shape of the features of the surface. So it means that if you're measuring some really small objects by the tip, which is really sharp, maybe you will see not exactly the properties of the sample, but the properties of your tip. For example, this is a nice image from asylum research, and this is a demonstration how absolutely the same surface profile can behave, can look if you measure it by the different cantilevers. So if you have a really super sharp tip, so you will see the small features of the relief. If you have some wide pyramid, you will see some changes and triangle elements on the surface. And if you see some really wide parabola, you can mostly measure the profile of your tip, but not the profile of your sample. So you should take into account these features of the IFM resolution. Okay. There are some different, so for sure there is different options. So for the cantilever radius on the market, so you can buy anything now if you have the money, but the problem is that the super sharp tips, it's usually very expensive. This is the first point. And the second point also that when the tips are interacting with the samples, they can change the geometry very fast. So it means that it doesn't mean that you should buy every time only super sharp tips. So you should really see on your task. So if you need to measure some not really sharp features, maybe it's better choice to use standard tip, or even maybe wide tip, or something different like a colloidal tip, for example. The colloidal tip is a tip with the big particles on it, like in the image on the right side. And this specifically is done like a white object because it allows, for example, to study the biological objects where you don't need a really high resolution, but you should be careful not to damage the cells, because if you are measuring the living cells especially, it may change and even kill the cell. And the next point which I'm going to talk is the taping mode IFM, which also is very useful for applications, and I think many of you who are working with IFM also had an experience to work with taping mode. And taping mode is a bit different from the from the contact mode, because you work in a different force regime. And as you remember the slide with van der Waals force, we separate the region with attractive forces. So intermediate contacts usually operate with the attractive forces or attractive and repulsive forces, but not in the direct contact with the material. So typically in order to organize these interactions, this is not so easy, because if you just push on the tip, you will damage the sample. And for that reason, you organize the oscillation of the cantilever with the amplitude of 20 to 100 nanometer. And this amplitude can change when you interact with the sample. So we can see the video now. So this video from MTNT demonstrating the regime of the work of the microscope. So when you tip, oscillating tips, put in the contact with the sample, so it decreases in amplitude, and this means that if you go closer to the surface, your amplitude becomes smaller, and if you go in strong contact with the surface, you see that your amplitude becomes close to zero, and in that case, the deflection signal changes. So actually, this is the main principle which is used to operate the atomic force microscopy, technique mode atomic force microscopy. Okay, I will skip this slide, I think. What is the difference, the main difference between the contact mode and taping mode? So the major difference is the contact mode is operating with the deflection signal. So it operates with the bending of the tip and changing of the position of the tips physical. And in the taping mode, we work with the oscillation of the tip, and in that case, when we go closer to the surface, we just decreases an amplitude of oscillation, so the amplitude of deflection oscillation. So in absolutely analog of the contact mode measurements, we should, in order to keep the feedback and doesn't destroy a tip, we should keep some parameter constant. And in that case, it's not a deflection signal, it's the amplitude of the deflection signal. This is also the one main point that when we work in a taping mode, we keep constant the amplitude of the deflection signal. Why it is important? Because it really makes sense when you choose so-called set points, so the work point which is you usually put as a parameter to your system in order to determine the force of interaction between tip and surface. If you work with deflection signal and you work in a contact mode, so as we see before, decreasing of the tip surface distance leads to linear increasing of the force. So it means that if we put higher set point, higher deflection signal set point, you will increase force which you apply to the tip. But in opposite, if you work with the taping mode, so you organize your experiments in a different way. So you oscillate the tip and you have some free oscillation of the tip, as you see on the right side. On the left side of on the left image, on the right side of this image, you may see that there is some free amplitude which doesn't change in the beginning when we go left, so closer to the surface. And after some moment of the time, the interaction between tip and surface started to decrease in amplitude. And when you decrease amplitude to zero, you jump in contact and you work further in a contact mode. So on the right side, the same, the analog plots is done for the amplitude value. So you see that if you have free amplitude, and after that you will got some set point when your amplitude is decreasing, and then you got in full contact, so the amplitude become zero. So this is an example of some taping mode measurements, and you see that the real also can be done really nice. So with visualization of details, it's a pretty high resolution. So in the point of resolution, there is no big difference between these two modes. And what is more important, if you're working with some films, for example, for electric films or whatever, so when you do some contact measurements from the first view, it looks like you're really doing some normal measurements without any damage of the surface. So as you see on the first scan, you see some topography. It's a bit smooth, but it's okay. Yeah. But if you do later the second scan a bit wider in sizes, you may see, and if you do it in the taping mode, you will see that actually the area which you scan by the in contact mode was damaged. So you see some scratching of the places. And if you do the same thing in the taping mode, you see that there is no any damage to the surface, as well as the relief become more sharp. It means that you don't have any strong interaction, destroying interaction between tip and the surface. And that's actually makes sense for nanomanipulation. So if you need, you can modify your objects by the contact of the tip with the surface. And if you need just to visualize, you may use the taping mode only. And also the very important point is, in order to understand the taping mode, this is we use resonance frequencies in order to excite our oscillations. So when we talk that we have some oscillation of the tip, it's specifically done on specific frequency of the cantilever. So if we model the cantilever as a point mass model, so just a very simple model, so we will have one specific resonance, free resonance, and when you're measuring on this resonance, you have really gain amplification of the signal 100, 200, 300 times. And this makes sense. So this gives us a unique opportunity to measure really small signals by taping mode. And if we're gonna in more details, so actually there is no only one mode, free mode. So actually, as each vibrating object, so you have a different modes of oscillations, and all other modes also make some physical meaning and can be used as well for the amplification of the signal. It is very important that this oscillations spectrum you also can measure in a contact with the surface, and if you do it like that, so you can characterize the mechanical properties of the material, and this is so-called atomic acoustic force atomic microscopy mode. And specifically, you don't need another indentation, and you can measure the your material mechanical properties such as Young modulus with pretty high spatial resolution. And this is some examples also from asylum research. So you may see that this just topographic features of the sample on the top side, and you see that there is some changes on the position of the resonance frequency. This is contact resonance frequency. You see that there is some changes of these positions in different regions of the sample, and it actually reflects the different Young modulus of the material. If you plot these changes of the frequency, you can see that you can easily demonstrate the regions with the different mechanical properties across the surface. And also, I have not too much time. I also want to finish in some short remarks about jumping mode IFM. So in jumping mode IFM, it's also some specific mode of IFM which is developing recently, and it represents a combination of the taping and contact mode. So in that case, as we told before, we can measure the force distance curves, and actually we can do it really fast. So because we can use the scanner and we can excite the scanner by the low frequency signal, for example, with a frequency of 100 Hz. In that case, you will very fast retract and withdrawn tip. So you can approach and withdrawn tip. So it's a really fast process, and during this process, you can register the force force measurements. So the same things like measurements of force distance curves, but you do it really, really, really fast. And in that case, if you have a specific system which can analyze the signals with really high temporal resolution, which is now it's really become widely spreading, so you can collect big arrays of the data. So in that case, you can collect many force signal in a second, and you can collect all this data in the big massive, and after that you can do post-treatment of the collected data in the mathematical processing. And after that you may not operate in some feedback mode or doesn't feedback. You can organize feedback just with very fast acquisition and treatment of the force data. In that case, you can very carefully control the applied forces, and that means that you can apply much lower forces like in normal contact mode. So because you're controlling the baseline, so the line before interaction, you control the interaction immediately in the contact area. So, and you also can measure some adhesion. So it's actually you can analyze and extract many properties from that temporal dependence of the forces. As well, if you know where is exactly when is exactly tip interact with the surface in a time of the contact between surface and sample, you can capture some thermal properties and conductivity properties, so piezo response properties. So it is actually very powerful techniques which allows to control any interaction with the surface. This is an example of the images. So in each image of this, in each point of this image, you measure the force distance curves, and you can extract from these force distance curves some force signals, so reflex topography, some Young modulus, and you actually can have really high spatial resolution. In the bottom part, you may see the different images where you're measuring simultaneously Young modulus and surface potential. So actually, we can. This third mode is the most powerful because also you very carefully control forces and you exclude any lateral interaction with the surface. This is also very important because if your tip is fastly interact with the sample, so you use fast withdrawing and approaching, so you don't apply any lateral force, and you can really work with very hard materials like nano objects. You will not move them by the tip motion, which is usually happens in both in contact mode and in taping mode. And this is some comparison list of 3 major regimes of the atomic force microscopy. So in the contact mode, it's very easy to set up. You can have less contributions from the really features. So actually the disadvantage is that you applied really high normal and lateral forces, and you possibly can damage soft samples by the interaction of with tip and surface. And in taping mode, you have some less applied force, and in jumping mode, you actually have really minimal lateral normal force. You can precise control forces, and the main disadvantage usually is difficult to set up and a bit slower scan speed, but it is more or less now approaching to the scan speed of the taping and contact mode. This is the 3 major modes of IFM, and actually based on these modes you can construct any additional measurements. So for example, in a contact mode you may apply the voltage and measure the current, or in a taping mode, for example, you may apply the voltage and measure the force under the action of this voltage, so some electrostatic measurements. And in jumping mode you measure, for example, the Young modulus, or you can for example, heat your tip and measure the thermal conductivity. So that is why these three atomic force microscopy are baseline for doing further complication and measurements in atomic force microscopy. Some examples of the different modes I will give here, but I will not go in details. If you're interested, we can talk separately about that further. So the first example is the measurements of conductivity. So we can apply the voltage to the tip and you can measure the current. So this is just simple measurements of IV curves expanding on the mesoscale. And in that case, for example, in lithium batteries, you can see how battery discharge and charge. So because on the lithiation degree, the electric conductivity is highly dependent. And as well, you can measure IV curves and analyze in the same manner as you do it for microscopic materials. And the other option, for example, in taping mode, you can apply the voltage to the surface, to the tip, so between tip and surface, and you may see and collect the images of electrostatic interaction between tip and surface, and this allows to measure, for example, the distribution of the charge across the different special homogeneities of the sample. As example, here, this STO material, and you see the grain boundary between two separate grains, and you may see that there is a charge collected on the boundary between two regions. And which is also important, you can modify, if you scan this area with the contact mode, with the applied DC voltage, you can modify the electrical properties, and thus you can study how the relaxation of the screening process by the mobile charge is organized in this system. And for sure, there is an option of measuring piezoelectric properties as well. I know that many people on this conference work with the ferroelectric and piezoelectric materials, and this is especially interesting because the piezo response, and so this is a deformation of the material under the action of applied electric fields. So it's really high signal, and this allows us to see very precisely the position of the domains inside individual grains, the direction of polarization, and which is also very important now. So now the quantitative PFM measurements is rapidly developing, and it means that we not only measuring some contrast things like to see the different orientations of the polarization, but we also can quantify the piezoelectric coefficients with high accuracy, and we can, for example, extract the value of the polar phase and non-polar phase and compare them. And actually what we did in our specific researchers, we demonstrate that this difference, which the phase content extracted from X-ray diffraction and piezo response force microscopy is very, very similar. So it means that this method is highly interesting to measuring the phase distributions in the ferroelectric materials, for example. I think this is basically all which I want to talk today. So this is, I want to acknowledge these two companies which produce really nice microscopes, and they have really nice presentations on their sites, so you may go and by these links and check also the moments which I not mentioned in this presentation. So I want also to thank you everybody for your attention. I'm ready to answer on your questions if you have.
Thank you very much for good presentation. And okay, now we open for any question to Denis. Any question? What? It's not active. Okay, maybe I, because it's possible to ask you. What is what your opinion, maximum resolution of atomic force microscopy for piezo response?
Okay.
And
So,
what you know about these results?
yeah. So actually,
Maximum.
yeah. Oh, thank you. So actually, I understand the question. So it depends actually on the optical beam deflection system. Yeah. So it's actually differs a lot in the different microscope from Brooker, from Asylum research, and what I measured by myself was done on the best values were done in Asylum research microscope, so-called CIFER, and in the CIFER microscope, the sensitivity is about 10 femtometer per volt.
No. I'm asking about lateral resolution.
Lateral resolution. So
yes, lateral resolution.
Yeah. So lateral resolution depends on the tip, actually. So in order to have really nice lateral resolution, the best solution is to use the sharp tips. For sure, it's quite difficult because usually the tips necessary to make a conductive coating for piezo response measurements, and this increases size to at least to 15-20 nanometers. So you are limited in these values. On the other case, as far as I know, there were some progress in the creation of the so-called tips created by electron beam deposition, and in that case you can create quite sharp tips in the 1.5 nanometer diameter. So principally, if you work very carefully, you can increase your resolution, but it's still limited about 5, I think, nanometer. So this is maximum which you can achieve by this technique.
Okay, thank you. But what you say about this sensitivity for piezo? Yes, you say. But this is very difficult because this is relatively volume. In this case, it is okay. But what is best, on your opinion, microscope for PFM?
Yeah. So I mean, if you talk about sensitivity, it's not relative.
Yes.
It's not relative. I mean, it depends optical beam deflection system. So the CIFER optical beam deflection system is sensitive to about 1 picometer or 0.1 picometer, more or less like that. For sure, you can increase the voltage.
I think all microscopes have this sensitivity. This is in any case, it's very low. It's like angstrom.
No, I mean,
vertical resolution is very high for all microscopes.
No, it depends actually on optical beam deflection system, and if you, so I'm talking now not on the, if you want to talk about the maximal resolution, if you applied some large AC voltages, so you may have really small resolution like 10 femtometer per volt. But if you talk about the resolution of the optical beam deflection system, so it's about 0.1 picometer for CIFER, and for anti-MDT it's about 1 picometer. So for sure you may apply 10 volts AC and you will have the signal 10 picometer.
No, I think this is electronic. I mean, in any case, if we measurement extra signal in this case, this is depend from our electronic system. This not okay. No, maybe question. What is no any activity from?
There is also some question in the
chat. Could you please tell me about the importance tip? Okay. What is you think about? What is your knowledge about tip?
Yeah. So actually, the material of the tips is usually silicon. So if you're doing some simple measurements, I think you can start with the silicon. You don't need to do something else. But the most important thing is exactly do you study the soft material or hard material? In that case, if you're working with biological material, you may use the wider tips made of the silicon polymer balls which are deposited on the tip. So if you're working with some electrical modes, the other option is also to work with solid metal tips, for example. In that case, you can organize, because if you're applying voltages and you're measuring some current, for example, so you should have thermal stability of the tip and the stability of the tip for the high currents. And in that case, maybe it's better to use solid metal tips. As well, you can use also diamond tips. For example, if you work with very hard material and you are afraid that you can damage the tips, you can use diamond tips or tips with coating of the diamond. And in that case, it will not damage.
And for piezo measurement, diamond tip is good too. Yes. What is your opinion?
What?
For piezo measurement, for PFM, diamond you use?
It depends on the manufacturers. If it's really nice single crystal diamond, like it's
no, this is covered. It's layer diamond, conductive layer.
It depends on the manufacturer. For example, I like the measurements by nano sensor tips, which are really
I like too. Yes,
quite conductive. But if you are measuring by NMDT tips, they are not really conductive enough. They decrease, which is decreased the PFM signal and value of the
they use different silicon doping. Yes, different. What is conductivity? Conductivity is
because diamond you should dope the diamond in order to have conductivity. And if you do it not in the enough level, you may not organize. As well as NMDT tips also. I mean, diamond coated tips, they are too wide, and this also decreases the value of the piezo response.
You see, next question in chat.
Yeah.
So
for some reason, system does not allow me to use microphone. So may I ask?
No. It's possible now. It's possible to switch. This is our. You may try to do this.
I think it's done in the high vacuum conditions. So yeah, so there is possible, I think, in the Omicron systems to go with really small resolution, but my experience mostly in work and the normal conditions without a strict control of the vacuum. Yeah, so I mean, if you work with Omicron systems and a high vacuum, yeah, so in that case you will not react with the atmosphere, and if you carefully control the forces, in that case.
But what is your opinion? Last question: how people to go to atomic? But on extreme resolution, I think this is not possible. Yes.
Yeah, actually, I have slide here with lateral resolution. Yeah, this is.
No, okay, but this is very, very special situation. It is
like this one, like this is 2D
This is
materials,
like STM, yes.
Yeah, but this is a bit of, it's a kind of different equipment, so it's not like the AFM you can operate in your room. So it's
this is what is this is atom, yes?
Yeah, this is atoms in the
molecule,
maybe molecule, I don't know.
No, I think this is molecule. This is not atom. No, single molecule. I remember one paper only, maybe with visualization of single molecule. But in IFM, it's difficult to do.
So, Sir, please tell me.
It's not an extreme. It's not. No, 1 nanometer. I think this is maximum.
Yeah.
Okay. Any more questions?
Yeah. The last question is how to maintain tip of IFM and damage. So first, I suggest to use before any measurements on the contact mode. If you need the contact mode, you are doing measurements in taping mode in order to see the region which you're gonna study. This is the first. The second is to control the forces. So this, which is I told before. So you don't need to put some set point values as it is written in the manual or something like that. You should carefully check what is the sensitivity of your system and what is the force spring constant of your tip, and you calibrate, you understand what kind of force you apply. And for example, for my materials, I work with the ceramic materials. I know that the application of the force about 1/200 of nanonewtons is enough to keep tip safety. But it's for sure depends on the sample. If you work with some more stiff materials or materials with higher lift, maybe you need to use smaller forces, but at least you should control it. And the other option also to use jumping mode, because jumping mode is very safety for tips, but it's not incorporating no microscope, so this is the problem.
No, yes, but yes, stability of tip is this is a problem. Yes, and especially if you use contact mode. Yes, it is.
If you carefully control the forces.
No, and I think important in this cases is that important roughness. And
Yeah.
if smooth you face, okay, in this case it is more stable. But if rough, and maybe gain is important.
Yeah, I also want to mention that I usually use also the slower velocity for contact measurements. So,
yes,
for example, for contact measurements, I use about not higher than 9-10 micrometer per second. And for taping mode measurements, I can increase it up to 15, 12, or 20 micrometer per second. So this is also a very major point. If you do really fast scanning, so you have a lateral force, and this lateral force will destroy your tip.
Okay, thank you very much.